No, I don't work there. It's just called.
Okay, so we're ready to talk about this one together. Okay, oh, sorry. So, first things first, let's get it set up to draw. Okay, so we have the three isotopic forms. Let's zoom into the problem. So we know that M1, I'm going to label this as 1, neon 20 is 1, neon 21 is 2, and neon 22 is 3. So we know that M1 is 19.9924. Percent 1 is 90.483%. M2, I don't need to switch colors, right?
No.
No, okay. M2 is 20.9938. U for AMU. The percentage of 2 is 0.271. Okay.
And then asking us to find
The atomic mass of neon 22. So the mass 3, let's see, we're not given the mass 3, so that's a question mark. The percentage 3 is a question mark, but we can figure that out.
yes.
And the average atomic mass, M average, we can get from the periodic table.
Okay, that's
So if we go to the periodic table and we go and find neon, we get 20.18. Of course, this periodic table is a little bit less precise, but it'll serve its purpose. 20.18 AMU.
Okay.
Now, all of these percentages, when we add them together, should be equal to 100. So as a result, we can figure out this percentage 3, and percentage 3 is equal to 100 minus 90.483%. Minus 0.271%. And if we punch that into our calculator,
9.246.
let me punch it in just to be 100%, just so that way. Okay, and that gives us 9.246%. Oh, you're welcome to come in on the side. Oh, okay, perfect. So we have the percentage 3. So I'm going to write that down. So we have 9.246%. Perfect. Okay, now let's plug in all of this data into our percent abundance equation. So the average atomic mass, which is 20.18 AMU, is equal to the mass 1, which is 19.9924 AMU, times the percent abundance, which is 90.483%, divided by 100, plus the mass of isotope 2, which is 20.9938 AMU, times the percent abundance of 0.271%, divided by 100. Let's now adjust our view a little bit. Okay, and then finally, plus the mass 3 times the percentage 3, which is 9.246 over 100. And as you see, this is a long equation. Let me move over a little bit to the left, so that way I can put a percent sign at the end. Okay, perfect. So this is our long form equation.
Yes.
Now, we only really have one unknown, which is mass 3.
Correct.
So our next step, what we're going to do is we're going to resolve out all of this algebra, and then we're going to rearrange the constants to get mass 3. That's how I like to do it for these sorts of problems, just because if I go with a strictly algebraic solution, it looks like a mess. Okay, so we have 20.18 AMU, and I'm going to bring both of these terms to the left-hand side. So I'm going to subtract them out after I've punched them into my calculator. So we have 19.9924 times 90.483 divided by 100. So we're going to subtract, this number here is 18 0.0897 AMU. We're retaining excess sig figs to avoid
Oh, okay.
issues with sig fig rules. And then we're going to subtract this term as well. So we have 20.9938 times 0.271 divided by 100. It's really small. That's because the isotope is not very abundant. 0.05689 AMU. Okay, this is equal to mass 3. And what we're going to do is we're going to move this 9% and 100 over via multiplication. So we're going to multiply this entire top portion by 100 to cancel that out. And then we're going to divide it all by 9.246%.
Okay.
And if we punch this into our calculator, 20.18 minus 18.0897 minus 0.05689 divided by 9.246 times 100 gives us a mass 3 equal to 21.99 AMU.
Mhm.
Okay.
If I did it different, but I got the same answer.
Yep, that's perfectly fine.
Mhm.
Where we're wrong, I didn't grab the